Yeah, it's okay. I just want to make sure it's
Yeah, I think I just basically use
I just remember
I didn't get her answer. Seems reasonable. Sure that's the right number. Okay, so we got homework for coming in today, and then I have one grade for you passed around, and I think these are alphabetized, looks like it. 30.
you were riding your bike
Pass them up, come on. Time.
I'm sorry.
Do I have all the homework? Okay. You got quiz today and recitation, and then our third exam is Thursday, and it's my priority right now to start getting you preparation materials, whether that's outline or I may put up just a bunch of review sets on my math lab. That way you can work problems and then have immediate feedback. Okay? So I might not be able to get that all to you like today or tomorrow, but I'll just start trickling stuff out. Okay, so look on Blackboard and keep looking as I continue to update what I'm giving you to help you prepare for Thursday's exam. Any questions? Okay, so we're back to talking about big picture stuff, and next week we're going to formalize what's called the fundamental theorem of calculus. Fundamental theorem of calculus, it ties together everything we've been working on all semester. So what we do today is kind of, we're moving towards the fundamental theorem, and this is looking at the big picture of a lot of what we've done. So on Wednesday, we came up with this result, that if you start, in general, if you're starting to accumulate from A, so we're going to accumulate from A up to X, and X can change, right? So if we want to start, say, accumulating from some fixed value C, okay, are we ready to start?
Yeah.
Are we sure? Okay. So if we want to start accumulating from, say, a fixed value C, we found that that was just the accumulation up to X, right? minus the accumulation up to C, and that will give us the accumulation from C to X, which is represented by our open form of exact accumulation. So what we're talking about now is getting closed form exact accumulation. So in the whole first month and a half of the course, we developed this open form exact accumulation from rate. That's all that stuff we did. Now we're talking about getting closed form of exact accumulation. Okay, so right here, what does this represent? Not what does it equal, but what does this represent? What is the meaning of this right here? Can someone describe what the meaning of that is? We all should be able to. Okay? Who wants to go for it? Will.
It's the integral from 3 to x of the function 2t.
Okay, so kind of that's what it is, kind of reading it explicitly, but what is this thing? What is it? You want to keep going? Adra? Yeah.
The accumulation from starting at x and ending at 3, and then at the rate of 2.
The rate of 2t. So accumulation, she said, starting at x, ending at 3, if the rate is changing by as 2t. Is that right? Yutong.
The accumulation starts from 3 and with x with rate of 10 of 2t.
Yeah, so starting at 3, ending at x. Okay, is this a particular value or is this a function? And what makes it a function? Yeah?
You have an input and an output.
Yeah. So what is the input and what is the output?
Well, the input is from 3 to x, and the output is the accumulation.
Specifically, what is the input though? What is the one quantity that's allowed to change? Joe?
T or x. T is like small I times. Input is
Okay, but which is the input? What is the varying input that gives us different outputs?
X.
And what does x represent, Connor?
It's just like an x. It's just an x value. Like, because you have 3, but then from 3 you keep going up, and then whatever point you're on is the accumulation from is the difference from 3 to that point.
Okay, almost there. So we're going to start accumulating at 3. And where are we going to stop accumulating? So a variable x, that's the input, where we stop accumulating. That's what can change. That's what we're saying is variable. So I might decide to stop accumulating at 7. Now, if I start at 7, do I get a number or do I have a function? What's that? That's a number, right? That's a number. So then what does t have to do with it? What is t? If we just get a number, so I'm going to plug in 7 for x. Now I'm going to get the accumulation from 3 to 7. So what's this t represent? Okay? Remember, how do things accumulate? What is accumulation about? Yeah, bit by bit. And so in order to keep track of and sum up all the bits, we need this t, right? We need t to keep track of where we are along the way as we're adding up bit by bit. But what makes it a function is where we're going to stop. Where we're going to stop. Once we choose that stopping point, then we get a value. We get the accumulation from 3 to that stopping point. Okay, so is this open form accumulation or closed form accumulation? This is open, but now we have a way to write this in closed form. Sam?
It would be f of x minus f of 3.
Yeah, so it's the accumulation up to x minus the accumulation up to 3 is the accumulation from 3 to x. And so how can we write that truly in closed form? So what does that equal? What's that? Isabel? X squared minus 3 squared. Okay, so rate, and now we have closed form accumulation from rate. Closed form accumulation from rate. But what does that require that we, in order to do that, what did that require that we had? So this is a closed form accumulation from rate. But in order to get that, what did we need to have? Yeah, we needed to have the accumulation function that gave us that rate. And then now we can build any accumulation function from that rate. And now we can express it in closed form, having that original accumulation function from which we had that rate. So it's like a big circle, you see? It's like a big circle. So we'll go through this slide again. Okay, so this is what we did. Whole first part of the course, month and a half. From rate, we developed open form exact accumulation. And in general, what kind of thing was that? What was our symbol for that? What was it? I think you're saying, I couldn't hear. Integral, right? Integral. This is our open form accumulation from rate. And then we said, okay, what if we started with accumulation function? We used the open form of rate from accumulation, which was f of x plus h minus f of x, right? Rate of change in y over change in x. And using the open form of rate from accumulation, we developed all these rules for closed form. And that was our mastery test, right? Our mastery test was we came up with all these different ways to quickly generate closed form rate functions from closed form accumulation functions. So really on the left there, that's one and the same. Those are both closed form rate. So now there's only one more piece to this puzzle, and can we get closed form accumulation from closed form rate? And we just saw that we can do it. Okay, but we can do it when we have the accumulation function from which that rate came. So whenever we know an exact accumulation function, we can get its rate of change function, and then we can build any closed form accumulation from that rate. Okay, so this is kind of a complicated idea. So go back and review on the video. Think about it and go over it several times because it's not something that comes naturally. Okay, so let's practice again here. So there's the rate from this. So what I want you to do is write the open form. Say starting at 1. Write the open form accumulation for this rate function, beginning accumulating at 1. Jimin, did you get it?
Yeah, I think so.
Tell me, can you say it in words?
Integral from 1 to x
Okay.
of 24 t to the third n e to the sixth times e to the sixth t to the
Okay. Is that what she said? That's it, right? Starting at 1, accumulating to x, so that's open form. So now, write it in closed form. So write the closed form version of this accumulation. Calvin.
I got e to the 6x to the 4th minus e to the 6th.
E to the 6x to the 4th minus e to the 6th. Agree with that? Yeah, that's just f of x minus f of 1. Anybody have a question? Does it make sense? Okay, here's another function. Accumulation function. Find the rate of change function. Go. So I sense that we're getting rusty on derivatives, and we're going to need derivatives desperately here to know them well. So Patrick, you're up. Did you get it?
I think it's 1/2 times e to the negative x squared to the negative 1/2 power.
Okay, can I write it this way?
Yes.
Okay.
Multiplied by e to the negative x squared times negative 2x.
How did you do? How did you do? Okay, so yeah, like I said, I've sensed that we're getting rusty on that, and now's the time to get better at it. You'll see in a second, okay? We really need to know our derivatives. And I'm not big complicated ones with lots of quotient and chain and product rule. That's important, but just kind of basic ones like this. Maybe this is what, double chain rule, okay? Or even simpler. We just really got to know them quick and be able to get them out quick. So any questions on this one? Square root is 1 over 2 times the square root, and now times the derivative of the inside, which is another chain rule. So derivative of e to the something is e to the something times the derivative of the interior function. Are we good? Okay, so now I want you to write the accumulation function starting at -2 in open form and then in closed form. Nick, did you get open form?
It would be at the integral from -2 to x, 1/2, uh, 1 times 2t e to the -2 over 2 times square root e to the -2 squared.
So our rate function, right?
Yeah.
Is that the rate function? So does our rate function simplify to that? Just do we have a 2 on the top and the denominator?
Yes.
Yeah, so we can just write it that way. And then, so that open form then will be this, from -2 to x of the rate function dt. So it would be that thing with t plugged in for x. Okay, closed form. Saskia.
I got the square root of e negative x squared minus the square root of e negative 2 squared, so e to the 4th.
Okay. So I gotta type all this in. Is there an easier way to do this? What's that?
You can do f of x minus f.
Can I do f of x minus f of -2?
Yeah.
Yeah, so you're absolutely right. But with the technology, we've defined what f is. F is that function. So let's use it. Let's graph the open form first. So there's our open form of this function. Okay. What do you notice? So where are we starting to accumulate? Where does this start to accumulate? And what do you notice about -2? Roman.
There's still some accumulation to the left of -2.
But what about at -2? So if we're start,
0.
what's that?
At -2 it's 0.
And so does that make, so how does that make sense? That the graph goes through the point -2, 0. How does that make sense?
Oh, you're still asking me?
Yeah, sure.
Oh. Is it because that's where it starts at? So that's where you're going to start accumulating?
Yes, we start accumulating, so
Oh, that's our starting point at 0?
so how much have we accumulated? If we're starting at -2, then how much has accumulated at -2?
0.
Nothing's accumulated yet, right? So it's after we start moving to the greater than -2 that we start accumulating. Okay? So if I graph the closed form, what should we see? Same thing. Okay? So there's just the closed form. There's both. There's the open form. Anybody have a question? Okay, so everything we're gonna talk about now is really the same thing. We're just gonna add some new language. We're gonna add the idea or the terminology antiderivative. Okay, so this is the ideas really aren't new. It's just again a new terminology. So suppose f and g are functions. If g is a derivative of f, meaning that g is the rate of change of f, then f is called an antiderivative of g. Right? It's just putting the car in reverse and going back, right? So if forward is derivative, so we're starting with a function. If we do its derivative, then the function that we get, so then how does the original function relate to the function that we get? That's its antiderivative. So this is the derivative of f, so f is the antiderivative of that derivative. How does this relate to accumulation functions and rate of change functions? So how can we relate that to accumulation and rate of change? Calvin?
Antiderivative is the rate of change, or you're getting the function from the rate of change, or the accumulation from the rate of change.
So he said finding the antiderivative is getting an accumulation from the rate of change. Agree with that? Yeah, because over here, what kind of function is this then? Accumulation, and on the right, derivative is rate of change, right? So this is what Calvin said. Every accumulation function is an antiderivative of its rate of change function. Okay, but what we've been seeing here is that given a rate of change function, we've got more than one antiderivative, more than one accumulation function. It's like we have to decide where we're starting from, right? We can start accumulating from any value of the rate of change function, and it gives us a different accumulation function. So, given an accumulation function, how many rate of change functions does it have? Will says one. Yeah, just one, right? There's only one rate of change profile for how something accumulates. There's not more than one. But given a rate of change function, there's lots of different accumulation functions that could change according to that rate. Yeah, ask me, Will.
Because when you go from accumulation, you take a derivative, the constant is
That's kind of the algebraic result. So because of what we're saying, that's true. It's not the other way around. Does that make sense? Yeah. Yeah. Questions on this? So just new language, okay? Antiderivative. So we've been finding accumulation from rate. Well, that's the process of finding antiderivative. So here's a rate of change function. 4x cubed. What does this represent right there? So what is the integral from 1 to x of 4t cubed dt? What's that? Nathan, can you describe what that is? Okay. Specifically? Yeah, that's right. Specifically, what open form accumulation function is it? Jenica?
The one from starting at 1 and ending at x at the rate of 4t cubed.
Awesome, right? So that's the accumulation starting at 1, ending at x, if our rate of change function is 4t cubed. Okay? So now, write that accumulation function in closed form. That's open form, so can you write it in closed form?
You would have to take the
There's something different here, right? What's different about this now? What's that?
We don't have the function.
I didn't give you the accumulation function for the rate, but that doesn't daunt us. That doesn't faze us. We can still handle it. Right? Connor?
Would it be, well, wouldn't the antiderivative be t to the fourth?
Well, so antiderivative would be in terms of t, or
Or, I mean, x to the fourth?
yeah. So really, now we're saying I didn't give you the accumulation function, but can we get it? Can we come up with it? Right? So it's really a matter of really knowing your derivatives well. To know what this accumulation function is, to see this as a derivative. The derivative of what? X to the fourth, right? X to the fourth gives us this rate of change function. So write it in closed form. Jack, did you get it? Yeah.
You're at x to the fourth plus 5c. Plus c is there to be any constant.
Okay, how about from what we're learning? What would it be? X to the fourth? Yeah. Kim?
Minus 1.
Minus Where does the 1 come from? 1 to the 4th, right? Closed form comes from the accumulation function that has this rate, right? X to the 4th minus 1 to the 4th. Okay, so write it in closed form. Is true or false? This is an accumulation function. True or false? I mean, an antiderivative. True or false? This is an antiderivative. True or false? That's an antiderivative. And if so, it's an antiderivative of what? Oh, I stumped you there. Is this an accumulation function? Or, sorry, is it an antiderivative? Anyone saying yes? Anyone saying no? Those who are saying yes, what is it the antiderivative of?
Accumulation function.
4x cubed. This is an antiderivative of 4x cubed. So write it in closed form. Sam, tell me.
X to the 4th minus negative 5 to the 4th.
That's it. See, if this is an this is an antiderivative of that, right? Why? Because 4x cubed is a derivative of this. If we were to take the derivative, what would we get? 4x cubed minus 4 times negative 5 to the 3rd, right? Jennifer, minus what? Why? It's just a number, okay? So, this is an antiderivative of 4x cubed because its derivative is 4x cubed. So therefore, this is an antiderivative of 4x cubed. Here's another antiderivative of 4x cubed. Write it in closed form. Dalton. Take its derivative. Kirsten.
4x to the 3rd minus 0.
What's up? Okay, so here's a new terminology. The improper integral, so if you don't have, if there's no starting and ending point specified, and it's just written, say, in terms of x like this, or in any variable, there's no starting or ending point, it's called an improper integral. Improper. It represents all antiderivatives of 4x cubed, every single one. So we can, it represents starting and accumulating from any place, starting accumulating from anywhere, and ending your accumulation at x. So that represents all the antiderivatives of 4x cubed. So, if we're starting at a, then the closed form would be x to the 4th minus a to the 4th. Okay, and so it's subtracting out the accumulation up to a, then will always be some constant value. Okay, so we can just say that's plus c. So that's where that thing comes from. So in general, the improper integral of a rate function is f of x minus f of a. So this represents what? Every antiderivative or accumulating starting from any point a And so we can just summarize that as just f of x plus any constant. So what does C equal? But in terms of accumulation, where does this value C come from in terms of accumulating? Yeah, Kim? No, not quite. Where does this value C equal? Joe?
The starting point of accumulation. So it's like starting the graph at $1,500 or whatever, that'd be $1,500 starting point.
Okay. That's true. What else does it equal? And so what is that? So where does that come from? So where that value? Yeah, it's look, it's this right here, right? It's the opposite of how much you accumulate up to A. Okay, so this process of finding antiderivatives, it's not a whole new set of rules. What is it about then? It's not about developing a whole new set of rules for finding antiderivatives. Rather, it's about really knowing your derivatives well, and so now we're putting it in reverse. So by looking at a function and saying find its antiderivative, you have to see that as a derivative, and you have to say what function has that as its derivative. So this is like it's a next level of difficulty in thinking, because you have to kind of imagine what function, if I took the derivative, would I get that? Okay, so in order to make progress at that, you have to be really good at your derivatives. So let's start with that. So I have a review sheet of derivatives. You should be able to fly through these, but I have a feeling that we're not 100% confident, so let's practice. So on the top of this sheet, right, find the derivative in big letters, because we're going to get to another sheet that looks just like it. It's going to be going backwards. Did everyone see the homework? Stack. So graded homework. Okay, so it should be rapid fire, but check with each other, make sure you're doing it right. So this is your finding the derivative of each one of these. What's the calculator for? So I'm gonna lag you a little bit so you can check. Once you've done. I'll put the first three up there. Okay, there's no quotient rule on this page. If you're approaching something with quotient rule, you're taking the long road, okay? Everything can be done without quotient rule. Okay, put some more up. Put this underneath, don't look at it yet. Put this underneath. Yeah, sure. That's right.
Oh, that's right.
The ones that look like a fraction, look like quotient rule, you start by rewriting them without a fraction. Start by rewriting them without a fraction. underneath. There we go. Okay. So like this one, how can you do this without a fraction? It's the same as 1/5 x squared. It's the same. That's what you have to be able to do quickly, or else you'll get stuck. All right. This one is negative sign radical x over 2 radical x. This one is 2e to the 6x times 6. Negative 6 over x. Okay, so here's what I was talking about. This next one, you have to see this as x to a power. What is it? X to the negative 3/4. Now we're ready for the derivative. Negative 3/4. X to the negative 7/4. Whoa. Questions on these first ones? I'm going fast here. Can I erase them? We good? This one will be e times x to the minus e minus 1. Again, what is this? No more not as a fraction. 10 x to the minus 21. So it's negative 210 x to the negative 22. Same thing here. What is it not as a fraction? Negative x to the negative 1. So it's x to the negative 2. Okay, so we really have to have those rules down so that when you look at something and you're asked to find the antiderivative, you have to see, this is the next page, you have to see that as the derivative of something. And you're applying the rule backwards to get the original function. Alright, so take the first one and turn it over. Don't try to compare it to the first one. So take the first one, turn it over, and see how many you can get. So now I'm giving you the derivative and asking you to find the antiderivative. Which means you really have to know your derivative rules. Okay, so on the top of this page, right, find the antiderivative. Make sure we got those two pages straight. So find the antiderivative on this page. Okay, and so then this will be part of the homework since we're out of time. But it's really about seeing that as the result of taking the derivative and going in reverse, getting back to the function that has that as its derivative.
Are these gonna be on the quiz?
Nope.
Yeah.